Differentiation, we're going to look at limits in the first instance, and then we're going to move on to differentiation and what it is. If you look at this function here, limit of this thing here, this function, x squared plus 1, this is LIM, it's just short for limit. It means as x gets closer and closer and closer to 3, as x tends to 3, see the arrow? So it approaches 3. On either side of 3, it just gets closer to 3 in any way, shape or form. What values does this have? Well, clearly as it gets closer and closer, I hope you can see that that would tend to get closer to that value, wouldn't it, which is 10. And that's easy to see, isn't it? And here, if x tends to 2 and gets very, very close to 2, the limit of this function, the value of the limit, would be 3 times 2 minus 1, which is 5. And here, as x tends to 6, 6 minus 12 over 6 is 2, 6 minus 2 is 4. So I hope you can see those, that it's very easy to visualize what's happening there with those simple limits. On the other hand, if you look at this one, as x gets very, very large, this is the symbol for infinity, plus infinity this means. So if it were 1,000, you'd have 4 minus 1 over 1,000, which is 0.001. So that would work out at 3.999 if x were equal to 1,000. If it were 10,000, it would be there. If it were 100,000, it would be another one, wouldn't it? I think. Yeah. So can you see that number was approaching the value 4? So in the limit, as x tends to infinity, this gets very, very small. It's 4 take away a very, very small amount. And basically it goes down to 0, so it tends to, in the limit, it tends to 4. Here, if you look at infinity, this will get very, very large. If it were 1,000, you'd have 1,000, 1 over 1,000 squared, wouldn't you, if x was 1,000, which is really, really small positive. It's 0.00001, I think. And then if it were another one, it would be another 2 zeros, and another one would be another 2 zeros, I think. So again, really, really small number, minuscule positive number. So in the limit, as x tends to infinity then, 1 over x squared will equal 0. So we can visualize these sorts of values then. So here as x tends to infinity, this will be infinity plus 1, which is like a huge number. 3 over a very, very large number is very, very small. 1 plus a very, very small number is just a smidge above 1, so it tends to 1, doesn't it, in that limit. Here, x cubed, you've got infinity cubed. So if it were 1,000, if x were 1,000, you'd have 1,000 cubed, or 10,000, or 100,000, or 1,000,000 cubed. You're getting a huge number, aren't you? So this limit doesn't exist, but it does shoot off to infinity. So we write equals infinity, but there's no limit here really. It's just a word picture in this instance. So here, as x tends to 1, well, I've drawn a table with the values calculated. If you have x as 0, 0.9, 0.999, because we're looking at 1, so we're looking at either side of 1. There's very close to 1 from below. Here's very close to 1 from above. And you can tap in the values on the calculator. When it's 0, you'll get 1. When it's x is 0.9, put it in, and you'll get 1.9. And you'll get these values. So I hope you can see that as x approaches 1, can you see what happens? There, it just on this side, as x tends to 1 from below, it gets close to 2 from below, and on this side, it tends to 2 from above, doesn't it? But it gets very close to 2, as x tends to 1, here, somewhere in here. So this value we can see by inspection, we think it's going to be 2, don't we, as x tends to 1. Those values, 1 would be in here somewhere, and you can see these values just lie very, very close to 2 above and below respectively. So as x tends to 1 then, we can say that this function tends to 2, and we looked at that by the values and just looked at values either side of 2 and very close to 2. But if we did the algebra on it, this is the difference between two squares, x minus x plus 1. The x minus 1's cancel, and it just leaves x plus 1. As long as x doesn't equal 1 itself. So in the limit, as x tends to 1, we can put 1 in here. 1 plus 1 is 2. As x tends to 1. But don't forget that we can't put x equals 1 here. So we're only looking in the limit as x tends toward 1, and not the value 1 itself, because that function doesn't exist at 1, but the limit exists. Okay, and that's what's mentioned here. This is equal to that, provided x doesn't equal 1, because you'd have 0 over 0 in the above. So that's all that's saying. So let's move on to differentiation now. We've got our heads a little bit around limits. Y is f of x, the derivative dy dx is, this is what it is, the rate of change of y with respect to x. So let's take an example of y equals x squared. And we want to work out the rate of change at x equals 3. So here's the curve, and here's the value 3, and we'll add an h value. So increase h by a small amount. It could be either side, but we just, for pictorial purposes, we put h as small positive. And so we nudge along 3 plus h, and we get this point here. So there's A, there's B. So there's 3, and there's a little bit along 3 plus h. This is the y value at 3, which is x squared, so that's 3 squared, 9. And this is the y value height here at 3 plus h squared. Now the rate of change at x equals 3, the average rate of change then of y with respect to x would be the increase in y, this height, divided by the increase in x. That's the definition of the average rate of change, of how much this is changing with respect to this. So you divide this number by this number. So the increase in y over the increase in x is the average rate of change of y with increase rate of change of y with respect to x. Now this height is the difference between these two heights, isn't it? So I put that in there. And this distance across here, the increase in x, is the difference between these two, which is just h. Expand this bracket, we get 9 plus 6h plus h squared. This is 9, so it's just 6h plus h squared is left. There's an h common on top, cancel that out, and we get 6 plus h, or h plus 6. So if we look at the limit then, as h tends to 0, so you can think of h tending to 0 in either way, whether it be positive or negative, it just tends towards 0. The limit of this value then will be the increase in y divided by the increase in x, which we said was h plus 6 as h tends to 0, and we can now evaluate limits. That's equal to 6. So that's the derivative. It's the rate of change of y with respect to x at any given point. So at x equals 3, the derivative of y equals x squared at x equals 3 then. We put the value in, we got 6, didn't we? More generally then, if we repeat the above for a point x rather than just for x equals 3, we have dy dx. This is the limit. Dy dx is this limit, so it was 3 plus h, wasn't it, minus 3. But if we look at dy dx in general, not just at x equals 3, but at x in general, so we use the symbol x, then we write dy dx. So this is the definition basically for the y equals x squared, because y was equal to x squared, wasn't it? So instead of it being 3, we put x in, and we put them in as we did before. Remember, we expanded the bracket, x squared minus x squared will cancel, 2xh is the middle terms, plus h squared. There's an h common on top, 2x plus h. So the limit as h tends to 0, 2x plus h was 2x. And if we put in x equals 3, for example, we'd get 6, which is what we had before. Okay, so this is in fact the definition of the derivative. So this is more generally now, this is a given, it's a definition of the derivative. If you're looking at the picture, what is dy dx? It's a measure of the tangent or gradient at the point x. So here's a picture of a curve, y equals x squared in this instance, to illustrate this general definition. Here's the point x, illustrated here. Here's x plus h, and this height up here is fx plus h. That's the value there. And then this is f of x, of course, here. This is f of x plus h. So you can see the triangle that could be drawn around the curve, can't you? So if I was to complete that, the longest side there, you'd have that. So this, the increase in y would be the height, and the increase in x would be the amount across, and that ratio would give you the slope of the triangle. That line there, the slope of that line. But as h tends to 0, can you see how this triangle basically starts to approximate the tangent here at the actual point, which we can label A. So I hope you can see that as this triangle shrinks down, the slope of this tangent will come to approximate and tend towards in the limit a value of the tangent. So we say limit as h tends to naught of this is the derivative. And it actually gives the value of the tangent at x equals a. So if we put any input value here, you'd actually get the value at that particular point of the derivative, which is the tangent. So that's what it says there. Notation wise, we write dy dx. Sometimes we write y dashed or f dashed of x. They all mean the same thing, just different ways of writing the same thing. Now some rules. So here's the first rule then. We did it for x squared before, didn't we? And we found the derivative was 2x. 2 comes down, x to the 1 less than 2, which is 1. And that's the rule. So there's the rule in general. Just to cheat a little bit, if you did x to the 0 using this rule, say, you'd get 0. X to the 1 less than 0 is minus 1. 0 times anything is 0. So that would be 0, wouldn't it? And x to the 0 is just another way of writing. Anything to the power 0 is 1. So 1 differentiates to 0. Okay, so any multiples, it's a scalar thing, so any constant actually, not just 1, differentiates to 0. So I just wanted to illustrate that. Just to mention that. I'll come back to that in due course. So let's use this rule then, this simple rule. So remember what happens, the power comes down to ground level, x to the 1 less. So the 3 comes down, so write dy dx then. The 3 comes down to ground level, x to the 1 less than 3, which is 2. Next one. The 10 comes down to ground level, x to the power 1 less than 10, which is 9. I'll write this one over here. The 3.7 comes down then. X to the 1 less than 3.7 is 2.7. This is just another way of writing x to the half. Now it's in a more convenient form we can differentiate. The half comes down, x to the 1 less than half, which is minus a half. This, if we wrote it in indicial form, is x to the minus 1, isn't it? Now it's easy to see how to differentiate in this form. The minus 1 comes down, x to the 1 less than minus 1, which is minus 2, which you can tidy up by dropping this underneath and flipping the index, and that's often easier on the eye. This one, let's bring it up to ground level and flip the index. Minus 2/3, and now it's in a form we can differentiate more easily. Minus 2/3 then. X to the 1 less than minus 2/3 is minus 5/3. And again, you could tidy this up if you wanted, minus 2 over 3x, and drop the x down to be with the 3 and flip the index of the power using properties of indices. And you could write it like that because it's slightly easier on the eye. But these are the forms you want to get them into in order to differentiate them easily. In the form that is in this, looks like this, then it's easy to write down the derivative. Then you can tidy up at the end. Standard derivatives then, here's the list of standard derivatives. We've done the first one, and we said 1 goes to 0, but any constant differentiates to 0. Here's the x to the n, differentiates to that. Sine goes to cos goes to minus sine, tan goes to sec squared. Sec squared is 1 over cos squared because sec is just another way of writing 1 over cos. E to the x differentiates to e to the x, log x goes to 1 over x, and as we said, the constant goes to 0. So that's the standard derivatives then that we'll find. Find the coordinates of on the curve at which the gradient is a quarter. So y is equal to x to the minus 2, isn't it, if we write it in the form that's easy to differentiate. Now differentiate, we use the power rule, the minus 2 comes down, x to the minus 3. That's the gradient function. When is that gradient function equal to minus 1/4 then? So we've got minus 2 over x cubed is equal to minus 1/4. So let's work that out. So move the minuses will cancel, and the 4 can come up to be with the 2 to make 8, and the x cubed can come up, x cubed times 1 is x cubed. So cube root both sides, we get x equals 2, don't we? So when x equals 2, what does y equal? Well, y equals 1 over x squared, doesn't it? So it's 1 over 2 squared, which is 1/4. So the coordinate value where the gradient is a minus quarter is this. We'll do this problem at the end of the first question.